Hello everybody, I'm PY. So I work at Square on the API team. And one of my pet projects is called LeakCanary. So today we're going to talk about that. In the past I've talked about how LeakCanary is built. Today we're not going to do that. We're actually going to start looking into what we can do with all of this information that LeakCanary is doing and how we can actually fix memory leaks. But first, as with every talk, here, I encourage you to engage and ask questions, anything, even tricky questions, happy to take those. So let's start with sort of a story to kind of set the frame. So let's say we have a fictional engineer, and let's call him Steve. And he's a bit of an artist, and he wants to make a statement about how mobile apps, they kind of take, they steal the focus away in our life. You know, we're always like looking at our phone. So he decided to make an app and to have the user steal the focus from the app, kind of a revenge kind of approach. And so the app just comes to life when it's focused, and then that kind of dies down when it's not. And so he decided to use multi-window with that, and so to like, it's an app that the app is just the top part, the bottom part is Evernote, and it's just blue. And then when you focus outside, it becomes gray, and then it becomes blue. It's like the most amazing app ever. So he releases that on the Play Store, and obviously he gets a lot of downloads, right? And like so many downloads, millions of downloads, great success. And then it starts getting one-star reviews because of crashes. People complain about crashes, so he adds a crash reporter into his app and checks out what's going on. And it turns out that he gets a bunch of out-of-memory errors. Wow, so you got an out-of-memory error. What do you do? What's the solution to that? Well, they kind of start popping up in different places, so he realizes, what about just marking it as fixed, and let's just forget about it and move on with our life, and maybe it's not going to happen again. The problem is, it keeps happening, and over and over and over again with different stack traces. So then he hears about a library called LeakCanary, and how it's supposed to make everything easy and to help you fix those things. So he had, dependencies to use the library and then update his application class so that he just, it's 2 lines of code, it's installed, and then he uses his app again, and now things are starting to happen, like you use the app, you try to focus. I guess I need to start the video. And yeah, we're gonna wait a little bit. It takes a little bit of like 5 seconds probably, and then dumping memory, the app will freeze. Bro, you've probably seen that if you've used LeakCanary in the past. So what's going on? LeakCanary is acting now. So next thing you get is a notification, and when you tap it on the notification, you get this pretty thing that might be a little bit scary. Like, what does it mean? What are we looking at here? So let's pretend I'm Steve, and I'm looking at this, and like I have no idea what's going on, but I see this view here. It sounds like this is my code. Okay, I'm gonna just look into that, this neo-mob realism view, which it's actually the view that renders blue. It's the most important view in the app, and the way it kind of focuses in and out, it's just by registering an activity lifecycle callback and changing the alpha of the view based on if the activity is resumed or paused. Now, if you're a bit of an Android expert, you probably noticed that we're registering an activity lifecycle callback. And what does that mean? We're getting the application class, which is a singleton, and we're adding a listener to it so that every time an activity is resumed and paused, we learn about it. We get a callback. The problem is we're never unregistering that callback, so our view instance is leaking, right? So what's the fix? Well, fix sounds obvious. When the view is detached, just remove the callback from the application. So we fixed the problem. But did we really fix the problem? What did we do here? So I think what we did here, what Steve did, and what we all kind of do when dealing with this is that we kind of try to guess what's going on, and we see a bunch of classes that look familiar, and we jump into them, and we look at them, and we're like, oh, I think there's a leak here. So this is the leak, and we fix the leak, right? And sometimes that works. But when it doesn't work, you're by yourself, and you're like, I don't know what to do. This is probably just an Android leak, and then you forget about it and move on with your life. So intuition helps, but and that's what we're using here. But the problem with intuition is that it makes you take shortcuts. That's the whole point of it. But you don't want to take logical shortcuts, and you need to kind of step back, go back to the first principles, apply some sort of scientific method, because we're engineers. It's kind of what we do. So let's come back to school and talk about class. Well, so we have a class A, and then we have class B. Wow. And there's we're gonna class C, and we're gonna create an instance of class A. All right, that's pretty easy. So what happens when I call this method triumvirate at the end of it? Well, if I call this method at the end of it, A is garbage collected, because obviously there's nothing keeping a reference to A, so it's useless and it's going to be garbage collected. Or let's say garbage collectible, and it will be garbage collected in the future. Now, let's come back to A. Let's say that we also create an instance B and an instance C. All right, not very interesting so far. But then we add a B field on A, and a C field on B, and an A field on C. And still nothing, still the same, right? But now we're going to start setting references. So we're going to change the code so that A.B references B, same thing for C, and same thing for A. So we have these three objects, and they reference each other. Now, what happens at the end of this method? Well, again, the three objects are garbage collected, right? They all have incoming references to them, and they all reference other things, but they're just connected together. So when nothing else is retaining them, they just get garbage collected. Well, that's cool. Now let's add a static field, right? We're gonna make a static field, singleton, and we're gonna pass the A reference to the singleton. Now what's going on if I try to, when I leave the method, nothing gets garbage collected because the entire group of objects is held in memory. So the static A singleton here, it's called a GC root. That's what I've shown as the yellow box. It's something that's never going to be garbage collected. It's a reference that is never cleared. So you could think of static fields. You can also think of local variables on threads, or references held by native code, like binder, for example. So that's interesting. But let's zoom out and think about the Java memory. If you think about it, your entire memory is pretty much a bunch of GC roots that have references to objects, that have references to other objects. It is a directed graph. You can think of the Java memory as a directed graph. And so we can apply some graph theory to it, like some very tiny things. So we can look at the block of objects over here. They're not connected to anything. They're kind of on their own. They're islands. So they can be garbage collected, right? And they're gone. So an object can be garbage collected if it's not connected in some way to a GC root. And that's very important, because this is what creates memory leaks. So let's say that the red thing here is an activity, and onDestroy has been called by Android on that activity. So we know that it's useless at that point, and that nothing really needs to use it, and it shouldn't be in use. But it's still holding on to a lot of memory, and we want it to be garbage collected. And so this activity is held in memory because there's a path, there's a bunch of references that eventually reference the activity, and that's why it's kept in memory, right? So the activity is leaking. So if we wanted to figure out why it's leaking, we have to find a path from those yellow boxes to the activity. It's called a path to GC roots, right? So that's what it looks like in that example. There's, in the Java memory, usually you end up with an infinity of paths because there are so many objects that are connected together. So you could look at like 10,000 paths. That's not very helpful. What's more helpful is if let's say there's only one leak, one bad reference that's causing the activity to leak, then there is an infinity of paths, but there is one that is the shortest path that is guaranteed to go through that bad reference. So instead of looking at 10,000 paths, we can just look at one, and we're going to look at the shortest because that's less information to deal with. So this is the shortest path in that case. And then that's what LeakCanary gives us. The display that we saw, this is exactly what it's showing in a kind of a textual way. Now, this is interesting, but this is where like the entire trick starts to apply. Okay, we have this path, what do we do now? What we do is we identify the objects on the path that are supposed to still be in memory and the objects that are supposed to be gone. And it's not just going to be one. For example, maybe the top green one is the application class. It should stay around forever because it's a singleton. Maybe the first red one is a view class, and the second red one is the activity, and the view is detached, it should be gone. And so if we're able to kind of identify the ones that should be in memory and the ones that should not be in memory, then we can sort of split the path in sort of two areas. And we can identify the connection that's creating the problem, right? So what's going to happen is for every single leak, the top part is always going to be objects that should be in memory, and the bottom part is always going to be objects that should not be in memory. And the key part for you is to identify each of the two zones. It's not going to interleave, so the top is always green, the bottom is always red, and the place where it changes is where there's a bad reference that you need to kill. And if you kill that bad reference, then the object is not connected to a GC root anymore, and the whole thing can be garbage collected. All right. So that was a little bit of theory, and now we're going to look at a couple of examples. The idea is, I think it's nice in the abstract, but we need to kind of practice to get the idea of how to fix these things. So let's look back on the first example, right? We had this LeakCanary, like this very simple app. So the first thing is you start looking at that, and you might not be familiar with this guy here. There's like a $1. If I'm Steve, I just started writing Android apps, and I'm like, oh, what is this class that's named $1, and then there's a field called this $0? What is this? So let's get on to that. So we saw that code, and we saw that there's a lifecycle callback. It's actually an anonymous class, right? And that's what it is. So in Java, this might be obvious to a lot of you, but Java doesn't actually support anonymous classes. It's a lie. It's all a lie. You write an anonymous class, and then what it does, it compiles it to a real class, and it names it $some number, and the number is based on where it's defined. So the first one is $1, the second one is $2 in that class. And then the name of the field is going to be like this $0. So if we come back here, when we look at this leak trace, now we have a better understanding of what's going on. We can see that at the top, there's a class called ActivityThread. It has a field called sCurrentActivityThread. And that field points to an instance of ActivityThread, which has a field called mInitialApplication, which itself points to an instance of the application, which has a field called lifecycle callbacks, etc., etc., etc. It's kind of how you read these things, right? So, like I said, we can split the leak trace in two areas, the good stuff and the bad stuff. And once we're able to do that, we know that the place where things need to be fixed is where there's a difference between the two. So here that would be, if you look at you can see that the view should not be in memory, the lifecycle callback should not be in memory, but the list of lifecycle callbacks should probably be in memory. So let's start from scratch and kind of do it step by step. If I'm looking at something fresh, I know that my activity is leaking because that's what LeakCanary reported because the activity is destroyed. I also know that the application class is a singleton, and it's always there. So it's never leaking, right? So if I can say the application class is good, then everything above it is good as well. I don't even have to care about it. And then there's a view here, and we kind of know that the view should be gone already, but let's check that out. How do we figure that out? And so LeakCanary has a thing called share info, and it's going to basically share a bunch of text that gives you more detail. It's kind of a textual representation of this. It looks like that. And you can kind of see the same like references, blah, 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 the same view. But at the bottom, there's a detail section. And the detail section, it might sound like it's kind of crazy. It's just a ton of stuff, but it's all the values of the static fields and the fields in the objects on the chain. And so if you slide down to the view, which I have here, and we start looking at fields, we can see that there's a field called m_attach_info, which is null. So what is m_attach_info? Well, if we open the view class, we can see that the method called isAttachedToWindow actually checks for m_attach_info, so being null. So when m_attach_info is null, the view is not attached to the window. And if the view is not attached to the window, then it doesn't really have a business being around. It should probably be garbage collected, because who needs a view that's not attached to the window, right? That's kind of our hint that this view should be garbage collected. So we know that we can like go up and include the view, and then the callback being kind of tied to the view should also be gone. So we're pretty much back to where we were. I added the list, basically. So m_activity lifecycle callbacks, it's an array list. And then you can see that it goes down, and the array list is implemented by an array. And then the first element of the array points to the callbacks, right? OK, so that's good. So we saw the first principles. Let's get into more interesting leaks. So when you install LeakCanary and like you pass that in, you make an application and you have everybody in your company use the dev application with LeakCanary on, what happens when LeakCanary is triggered and a notification shows up? So you'd think people will sit down, bring it to you, fix it. Well, no, what actually happens is that you swipe the notification away and you just do something else and you pretend like you didn't see that there was a leak. Because it's kind of annoying and you don't want to like change what you are doing. So we had this problem and we thought of a way to fix it, which is to automate the leak reporting so that they would be uploaded in background. So that was great idea, but nobody wants to write a backend for that. I certainly didn't. So what we did is we decided to upload to a crash reporter and to fake a crash. So basically, you can fake a crash by making a fake stack trace. This is how you make a fake exception. Then you can then pass to a fake stack trace, to a crash reporter. And then we have, we use Bugsnag, and we had a Bugsnag leak uploader that converted the leak trace into a fake stack trace, and then it's uploaded to Bugsnag, which then gives us this. This looks like a stack trace, but it's not, right? You can see because like there is at javalang object, and then the method name is like 0, which is weird, or 97. But there's another tab where we actually added the kind of meaningful information. So the nice part here is that if you get 5 times the same leak, it's going to lead to the same stack trace, and then Bugsnag or Crashlytics is going to group it together. So you get grouping and counting, and you know the leaks that happen the most often. So that's really nice. But then there's another tab. Give me a second. Sorry. There's another tab which provides like the same useful information. So let's look into that one. What's that about? And if you do a quick scan, you could say, oh, there's support library in there. I don't want to know about that. Let's just walk away. But no, we don't want any leaks. So we're going to look into every leak. So let's start with the top. We can see that there's a looper at the top. And the field that's holding onto it is called main looper. So you're pretty sure that this is the looper of the main thread. And the main thread is around forever. The looper of the main thread is around forever. So that's good. And then at the bottom, we can see that there's the leaking activity. All right, that's easy. This one should be dead. Then we're just going to poke around. So let's look at the middle one. There's a class called runQ, and it has a field called mActions. And what is this? Like, who's ever looked at the code of runQ before in the room? No one. Literally no one. That's good. But Android is open source, so we're going to do that right now. Right, so we have the view root impl, which is actually the view that is at the roots of your view hierarchy. It's not exposed by the Android SDK, but that's how it is in the code. And runQ is an inner class of that. And runQ has a method called postDelayed, which basically lets you pass it a runnable, and it's going to wrap it in a handler action. And then it's going to just add this action to mActions, which is a list of actions. All right, that's easy. And then there's another method that's called post. and it just calls post delayed with a delay of 0, right? So far so good. So what it looks like is that when you call post, you're actually enqueuing a runnable into M actions. And when is it dequeued? Well, let's read the Javadoc. Javadoc says, the work is executed during the next call to perform traversals on the thread. So this is the view root. This is the one that handles the traversals that are going to measure your layout. And it's basically saying, I'm keeping things here until I get the next traversal. And then who's calling that? It says the run queue is used to enqueue pending work from views when no handler is attached. So this only happens when you're in between two traversals and there is no view hierarchy around to execute the work. So let's verify that. If we look at the view class and we open post on animation and post, we can see that the first thing it does is get the M attached info, which we saw can be null if the view is not attached. And if it's not null, post for real into the choreographer or the handler. But if it's null, get the run queue and post to it. All right, so that seems to confirm what the Javadoc was saying. So the idea is, at that point, we don't have a view. We don't have a hierarchy. The view is detached. It's not attached to a window, but we're posting to that queue. And next time we get a new view hierarchy, we're going to execute those things. And where is get run queue? Well, it's a static method. Where's the run queue coming from? So it's coming from this get run queue method. And what it is, it's stored in a thread local. So a thread local is it's a variable for which each thread has its own value. But for the purpose of this, you can just think of it as a static thread that's pointing to the run queue. Except every thread, as a static field that's pointing to a run queue, and then every thread gets its own. So then, if we look at the run queue method, then it's basically if the queue is not null, return the queue. Otherwise, create one, store it, and return it. All right, that's pretty easy. So that brings us to that, where we can see, we can start to understand the things that are below, like right here, that thread.local values. It's not the run queue field that we are saying, but that's basically how thread locals are stored on a thread on Android. So the run queue, it's a static field. It doesn't sound like there's anything wrong there. So it just holds on to a list of actions. So the run queue and its list of actions should actually stick in memory. So if you just go down there, there's like the run queue actions, the list itself, not the elements in the list, but the full list itself should be in memory. So that's kind of, we now have less things in there. So let's look at this weird class name, app_compat_delegate_impl v23. What is that? Well, it's an instance of app_compat_delegate. So it turns out that if you use the support library on Android, you have to extend app_compat activity. And what app_compat activity does is it builds a delegate and it delegates all of the calls to that delegate. And then you have different implementations of that delegate based on the Android version. And so because it creates an instance right there, when the activity is destroyed, the delegate should be destroyed as well. Right? There's one instance per activity. So we can come back here, and now we know that the delegate should be gone. Right, so that's the reasoning that you keep applying when you look at a leak trace. So let's look at the one above. So v9$1, so it's an anonymous class. So I talked about how there's a bunch of implementation, and v23 actually extends v9 eventually. So let's open the v9 class. And the $1 class is this runnable, minvalidate panel menu runnable. And then it gets posted on a view with post on animation, right? And so if that view was not attached, we already know what happens. You post on animation, the view is not attached, it gets put into the run queue, and it will be dequeued and executed the next time that there is a view hierarchy. But what if your activity is destroyed and the user goes away and there's not an activity for another 30 minutes? Then the runnable is still in the queue for another 30 minutes, and it leaks the entire view hierarchy. And so you're basically keeping the entire view hierarchy and all of its bitmap for another 30 minutes until you get some other activity. So it is a leak. And so the way you could fix that, I don't know that this is the right way, but one way could be, well, when the delegates know that the activity is destroyed, just remove the callback from from the run queue, basically. So this was an interesting sort of leak. We actually filed an issue. This is a real leak that we found last week. So I haven't seen any response from the support library team, but they're looking into it. So like, we need to give them time. Eventually, it's going to be fixed. It's not like one of the biggest leaks. But I encourage you. The reason I'm showing that is because I want to encourage you to do the same. Next time you find a leak, Android is open source. You can go, and even if it's not in your code, which, by the way, is still kind of likely to be in your code. Like most of the time, it's in our code, not in the support library. But if it's not in your code, don't just drop it on the floor. Look into it, look into the code, try to figure out what's going on, and then report a bug on the AOSP issue tracker. Because if we all do that, then we make Android better, and then everybody profits from it. All right. So let's look at one that's maybe a little bit harder. It was harder for me. I was really confused by it originally. So this is the new leak trace today. I checked to make sure that I wasn't like showing any bad names or any sensitive information that shouldn't be in there, but I think it's good. This is real Square code, so let's do the same. So I said don't use intuition, or rather don't use intuition to make logical shortcuts. However, intuition helps here to find one good thing to look at, right? Like there's a lot of references or a lot of objects here, and I kind of don't want to look at every one of them, because if I can find one in the middle and I know it's good or I know it's bad, then I can bring down the green part or bring up the red parts, right? So we're going to be kind of smart about this. And I can see that right in the middle, there's a class called passcode unlock view. This is a view, and I kind of know how to verify if a view should be around or not, right? We already saw that. So let's look at that view and check if it should be garbage collected. So same thing, we go to the details, and we can see that m-attached info is null. So the view is detached, and we can assume that it should be gone at that point, which is really nice because now we can just boop, make all that red. That's good. We know that we don't have to look below that. The leak has to be somewhere above that fault. Then let's keep going. Another anonymous class. So guess what? Anonymous classes, they tend to be very often present when you have a leak because of the natural, they always have an outer reference to the class where they're declared. So that tends to create leaks. It's not always the case. So don't jump to conclusions. But here, it's kind of an interesting one. It's called $1, $4, $1. So you can have like any number of dollars. It's because it's an anonymous class in an anonymous class. So let's look at that. So we have this passcode unlock view. What it does is we have a small utility method called wait for measure, where you pass a view and a callback, and it calls you back when the view has been measured. And so that's the first anonymous class that we're seeing. But the second one is where things are interesting. What we're doing is we're getting a request creator object, which is a Picasso object. So Picasso is our kind of open source image library to make it very easy to deal with images on Android. And so here, this is something that basically makes a request after the view has been measured. And you get a callback when it's successful or error. So, let's look at the Java doc of this request.into method. Because the Picasso guys, they're smart, and they're telling you what you should do and what you shouldn't do. So when you call into, the Java doc says, asynchronously fulfills the request into the specified image view and invokes the target callback if it's not null. Right, so far so good. But there's also a note, which is, the callback param is a strong reference and will prevent your activity or fragments from being garbage collected. Haha. So I was like, yeah, that's it. And it says also, if you use this method, it is strongly recommended you invoke an adjacent Picasso.cancel request called to prevent temporary leaking. So obviously, sounds like we forgot to do that. So I opened up the passcode and unlock view. And guess what? We were actually already calling cancel request. What? So at that point, I was like, okay, I don't know what's going on. I was kind of lost. I decided to take a look at Picasso, what cancel request actually does. And so you open Picasso, like that's the cancel request method. And essentially what it has, but it does a bunch of things, but it has a list of, a map of target to actions, and it takes your image view, which is target, removes it from the map, gives you the action back. And then it calls cancel on the action, right? And so what happens when you call cancel on the action? A bunch of things, but in the superclass, there's a Boolean called canceled, and it becomes true. And the reason I'm going there is, and what I do when I poke at the code is I look for state, because I know that then I can go and see if that state matches in the details that I have about the leak, right? So if I come back to the image view action, which is an action, then I can look at the state. Oh, cancel is false. Wait, I called request cancel, but cancel is false. It can't happen because request cancel sets cancel to true. This is very confusing. So it really looks like the leak is definitely there, but we have no idea what's going on. So this pretty much shows us that the leak is at basically, we can very easily reason. Now we know that the image view action should be gone. It's tied to the image view. The passcode unlock view should be gone. We know that the list of actions themselves probably should still be around. So we know that the leak is there, but we don't know why it's happening. And that's where things can get kind of annoying. Like, what do you do now? We found the leak, but we don't know how we created it. Well, we did another hack. So what if I could poke around the memory and like figure out more things? Well, turns out that's what a heap dump is for, which is what LeakCanary uses. LeakCanary kind of takes a shortcut and presents you the quick view, but you can do it the old way, which is by poking around in memory. So we thought, well, we kind of need those heap dumps when the leaks happen, so we need to upload them. But again, I'm too lazy to build a backend, right? I don't want to do that. So what do you do instead? Well, it turns out that Slack has a very nice API for uploading things, or chats, or whatever, and you can upload a heap dump to Slack. So, and that's true, we have a Slack channel that just gets a bunch of leaks reported, and you can see that it actually has a binary. So far, so good. Slack hasn't really reached out to us telling us to not do that. I'm expecting that someday they're going to be really unhappy, but maybe if everybody starts doing that, we'll see. Anyway, it's very nice. It's very practical, because then I go on Bugsnag, I just go there, I find the leak, and if I need more information, I go on Slack. So the thing with Slack is that it's hard to get that group view that I have on Bugsnag. But when I look for something specific, I just search in Slack, and then I download the binary, and then I have it. So I downloaded the heap dump from Slack. So we know that the first thing we do in this Picasso class, when you cancel a request, is remove the target from the map, right? So the map should not have that entry anymore. So let's look at the map. Let's search for this action object. So I opened the heap dump with something called YourKit, which I believe you need a license for that. There might be some free licenses. The other option is to use Eclipse Memory Analyzer Tool, MAT. I like YourKit for, I guess, two reasons. One, it works with Android heap dumps, and for Eclipse MAT, you actually have to convert them first, and then you can load them. But the other reason is that it is more beautiful. It feels better. I don't know. Eclipse just feels bad and wrong. So there's something about that turns me off. Anyway, so I started, it's easy. You search for Picasso, and something interesting pops up, which is, oh, there are two instances. Okay, I'll just look at the two. And so I look at the first one, and I see that the target to action map has 0 entries. Okay. And the second one, the target to action map has 1 entry, and one of those entries is the image view action, the one that I was kind of looking for. And you can see that the reference is it's an image view. So that's interesting. That means that the action is still in there and hasn't been removed, which maps with the idea that cancel was false. So again, don't jump to conclusion. It's not because we're seeing the image view action in here that this means that this is the cause of the leaks. We can see strong references here, but we see weak references here. It's a weak hash map. So this is not, it's by itself causing a leak. But it sort of plays into it. So we have that action, and it's not canceled and not removed. So it means that cancel request wasn't called, but we saw that we called cancel request. So I came back and I looked at this class, and I was like, okay, we do call that method. Let's look at what the Picasso instance is on that object. So I looked at the Picasso object, and then I opened it up, and I looked at target to action, and I see 0 here. So I had 2 instances of Picasso, and one of them had the target to action that I added, and the other one had 0, but the one that had 0 was the one that was referenced by the view. So it means that this is the wrong Picasso. Basically what's going on here is that we're getting a request creator from Picasso from another Picasso instance. And then we call cancel request on the wrong Picasso instance. So we're canceling nothing. And that's how we were creating that memory leak. So we were unregistering from the wrong one. I couldn't have figured that out. I maybe could have in retrospect, looking at the data, I found some ways that I could have done that. But it's much easier when you can poke around memory. So that's why downloading the heap dump eventually really helps you. All right, so I'm going to kind of go through a summary. So the general idea is don't jump to conclusions. You're going to see a bunch of classes that you know. Hold on for a minute, think about what it means, and then try to look for instances that should be dead. But the first thing is go back to first principles, don't jump to conclusions. Then try to find the objects that should be dead and the objects that should be alive. This is really what's going to help you figure out what's wrong. And then you can split the leak trace into 2 places, find the reference to kill, and hopefully you can fix your bug. So this is the last slide. You can rate this session, send questions, and that's it.